Hello and welcome in, everybody. Happy Wednesday. How are you all doing? My name is Brian. We're going to do some mathematics tonight. At least I think that's what I'm going to do tonight. I hope that's what I'm going to do tonight. And as always, if you guys have any questions and or concerns, get those mathematics questions up into the chat or into the Discord server, and we can answer those along the way. The last time that we were all together, it seems like it was just yesterday. So, what Saturday Night Fever? It's only Wednesday. Or do you mean my hiring outfit? Is that, are you making fun of my attire? How are you, Loins? Good to see ya. Well, I guess I can't really see you, but welcome on in either way. Always a pleasure to have you kicking around my attire. Yeah, totally. Let's see. Let's make sure we're good here. We're good here. Sorry, I froze on the backside there for a second. Might have a couple ads incoming for you guys just tuning in. But yeah, it was a big hiring day today, so we've been kind of busy interviewing candidates and all that good stuff. So, oh goodness gracious, I'm exhausted. I'm just mentally exhausted. I'm ready for Sunday. Sunday could not come sooner, is all I have to say. Sunday could not come sooner. What do we got? 153? 153, 10 times 15 plus 3. So the last time we were together, we were taking a look at Euclid 2019. That's the contest we're working on. And we were looking at question number 9. And I believe we were able to get A and B okay. We were starting to work on part C. Is it too risky? I mean, I could do a button up if it's a little... There we go. Maybe a little more professional if I... After the interviews were done today, I just let loose the tie. And then, went and had a glass of wine somewhere, and now we're here. And I think we had gotten to part C, and we were starting to do a little bit of work on part C here, right? So we had this multivariable function in terms of A and B. A and B are integers only, so that's important. And we know that A and B are positive integers, and that our function output should be an integer as well. So with those stipulations, we needed to prove that f of AB has to be a multiple of 3, which is actually kind of surprising and interesting. And I guess in both part A and part B, we ended up with answers of... We have a couple different actually answers, right? F of 1 comma 2 is 3, f of 2 comma 5 is 3. And I also believe that if we sub A in for B, we get 1 plus 1 plus 1, which is also 3. So we've seen a couple of situations here where the final answer is 3. And in part C, they're saying that it's actually a generalization. So it's possible to show that if we do get an integer result, it has to be a multiple of 3, which is kind of surprising to me. And I remember starting off part C by finding a common denominator and saying that a squared plus b squared plus 1 has to be a multiple of AB. And that's, I think, as far as we got yesterday. And I feel like I was thinking about cases, right? There, we had to look at a couple different cases, like maybe, how are we gonna dive our way through this? I mean, I feel like a squared plus b squared plus 1. I guess if A and B are both even, if we add 1 to that, wow, if it isn't the man, the myth, the legend himself, Mr. Sensation Black. How are you doing? Welcome on in. Hope you are having, I don't know, at least a bit more of a day than I'm exhausted today. My poor brain is just like. Anyway, welcome on in. My poor brain is just like, it's having a hard time finding stuff. You know what I mean? Like, I've been literally watching interviews about statistics all afternoon. So I'm ready to not think about statistics for a long time. And for those of you that might be new, welcome on in. If you have some math questions, feel free to throw them up into the chat and we can answer those along the way. Whoa, look at this guy, pumping some iron. On a normal day, wait, on a normal day. So on a normal day, I'd be pumping iron at this point, but I've only been back like 24 hours or something. Oh yeah, because it's pretty, I was gonna say, you're a little bit ahead of us, right? So, what is it, about 3, 4 in the morning over there? So I'm kind of wondering if we should divide this up into cases. And I think it's going to come down to the parity or the even and oddness of some stuff. I wonder if we could also... There's some interesting things happening here, right? Like, this number has to be divisible by A, doesn't it? That number also has to be divisible by B. So that's going to put some actually really interesting restrictions on the sum on the left-hand side of our equal sign. We might not even need cases, to be honest. We might be able to do something like this. We might be able to say, since A is a factor of A squared plus B squared plus 1. It's 337, 338. That's pretty damn early, man. That's pretty damn early. But either way, I'm very happy to see you back on the math circuit. Even if you're not doing math at 3:38 in the morning, it's nice to see that you're doing okay. If A is a factor, I mean, A is already a factor of A squared. If A is a factor of the sum of these three things, and A already divides A squared evenly, I mean, it must be that A divides the other stuff too, right? So A has to divide B squared plus 1. So A has to be a divisor of one more than a perfect square number, right? And we could, without loss of generality, we could probably stretch this out and make this work for B too, right? I think we can have a very similar argument. Yeah, in other words, I know that B is going to divide A squared plus 1. So A and B are both one more than a perfect square number. So why don't we start looking at some of our perfect square numbers? And let's see if there's a pattern with our perfect square numbers. So what are our first few positive perfect square numbers? So like 1, 4, 9, 16, 25, 36, and let's go to 49. So these are our first few perfect squares. And then underneath, we're going to write down one more than a perfect square number. So that's 17, this is 26, 37, 50. So, I mean, some of these are primes, some of them are composite numbers. But still nothing that's screaming divisible by 3 to me, per se. Do we have any other restrictions on A and B? I guess A and B have to start at the number 1, right? A and B have to be positive integers. So we know that A and B are at least 1 and are integers. So, I mean, all of the green numbers here, I mean, are definitely divisible by 1. I mean, if A and B are 1, I feel like that's kind of... Wait. I need to prove that FAB must be a multiple of 3. So our goal is to show that K is 3 times something, right? I should probably write that down. So this is our goal. If I can show that K is equal to 3 times whatever, we're done. Then that would imply that FAB is a multiple of 3. Right? In other words, I need this division here to give me a multiple of 3. Right? I wonder if we could go the other way. I wonder if we could... Could we start with 3x there? Could we start with 3? I don't think we can start with 3. I don't want to make that assumption. All I know is it's an integer. And I need to show that that integer has a divisor of 3. So 3 has to evenly divide into that integer. How do we do that? How do we do that? I don't know. Let's start looking at some divisors of 1 more than a perfect square number. So there's only 2 divisors here, and here, and here. 17, great number, by the way. Is 37 a prime number? I think 37's prime, isn't it? .37 is prime, so it has 2 divisors, 37 and 1. So we know A and B look like this, right? They have to divide 1 more than a perfect square number. But there's a mirror thing happening here, isn't there? So a has to divide b squared plus 1, and b has to divide a squared plus 1. Can we use that to our advantage? If a divides b squared plus 1, that means we can take b squared plus 1, we can rewrite it as a multiple of a, which is probably all we need. And then, should we... Let's see where that goes. Let's see where that goes. Before I start like working with like some of the crazy numbers and stuff, let's just see where this goes. So let me get rid of some of this stuff so I have some space. I feel like this question is at my pay grade. It's at my pay grade. I feel like I should be able to do this. So since a is a factor, let's replace b squared plus 1 with some multiple of a. Okay, and we know that this should be equal to k times a times b. So does this now give us a better relationship for a and b? Because I can factor out this a. And I can probably rightfully conclude that a plus m is equal to k times b. So I now have... Is that helpful though? Knowing that the goal is that k should be 3 times something? I don't know if that's helpful. And I mean, we could do it the other way too. So we could save the b squared, we could replace the a squared plus 1 as something like this. And we could conclude that b plus something is equal to k times a. I don't think that's super helpful though, right? I mean, we have a couple equations for k. We could equate them, I guess. But we're still going to have lots of parameters. So is there another easier way to see that this integer has to be a multiple of 3? Is there an easier way to do this? Is there something about adding up perfect square numbers that would be interesting to explore? So perfect square numbers can be even or odd, right? So I guess this is the other possibility. I could maybe start with this. Let's get rid of kind of, I don't know if this is really going to be helpful here. So let's just kind of go back to the drawing board. And let's say, what happens? Let's see if we can find some of these. Like, can I find some of these A's and B's that are gonna work? So let's try some A's and B's. So like, what if, can A and B both be 1, for example? What does A squared plus B squared plus 1 give us, right? That should be 3. And of course, dividing that by 1 will give us 3 over 1. So A and B equaling 1 is a possibility. What about 2 and 1? That would give me 4 plus 1, which is 5, plus 1, which is 6. Okay. That works. Does 1 and... I assume 1 and 2. I assume because this has like nice symmetry that this should work as well, right? This should be 1 plus 4 plus 1. So 6. A times B is 2. So... does that always work? So let's see if we can find... I think it always works, right? So if I can find an A and B and I swap the numbers around, that should work too. The other case they gave us was 5 and 2. I guess, yeah, I want to find a couple cases, I think, where this breaks as well, right? And I kind of want to see why it breaks. So A times B is 6. If I add up these square numbers, we get 4 and 9. 4 and 9, which is 13. So that doesn't give us a multiple of 3. So that one doesn't work. So I probably shouldn't try 3 and 2 because this is a symmetric kind of problem. But 5 and 2 work. What about 2 and 4? So 2 and 4, let's try 2 and 5. Oh, 4 plus 9 plus 1, right. 4 plus 9 plus 1, so 14. But that still doesn't work, right? That still isn't going to divide through and give us an integer number. So 2 and 4 would be 4 plus 16, which is 21. So 21 divided by 8, that doesn't seem reasonable. So they say 2 and 5 works, so that's going to be 4 plus 25 plus 1, which is 30, and we're going to divide by 10. Yeah, maybe that's it. Let's try 2 and 7. Do the inputs have to be prime numbers? That would be cool. That's a good thought. So that would be 4 plus, we're going to start getting into numbers where I don't want to add stuff. So 4 plus 49 plus 1, that's 54. Is 54 divisible by 14? My instinct says no. So it's not necessarily that the inputs have to be prime numbers, but that's a good guess. Although I have noticed that the ones that are working so far, so like this works so far, and obviously other than 1 and 1, which might be kind of a special case, I'm kind of curious about these other cases as well. So far we had one, other than the 1-1 case, we had an odd number and an even number. So I'm wondering if one has to be odd and one has to be even. So what if we did, like, is it possible to find another one? That's the question, right? Can we take like 2 and 9? 2 and 9 is 18. And what do we need here? 4 plus 81 plus 1, right? 86. That don't work. So what is it about 2 and 5? What's going on with 2 and 5? So 4 and 25. Let's try something just completely different. 3 and 5, so 9 plus 25, so 9 plus 25 plus 1. 35, this would be 15, that's not going to work. Can we find another one, right? If we could find a couple more and maybe try to figure out the pattern here, that might be helpful. A, B in those, yeah, A, B in those cases, A times B are always one more than a perfect square number. Oh, is this a Pythagorean triple problem? A squared plus B squared is C squared. Is this a Pythagorean triples problem? We need to find two square numbers so that when we add them together we get a square number. Two and 5, is that true? 1, not necessarily, right? 1, but it's that AB, it's that AB is always one more than a square. But yeah, so you're right. Maybe we should be focusing on A times B. We need A times B to be one more than a perfect square. So it seems to be, 1 squared plus 2 squared. 1 squared plus 2 squared. Yeah, that's not necessarily. But that also makes me wonder, like this is kind of 1 more than 1 squared, right? This is 1 more than 3 squared. Is there one that's 1 more than 2 squared? 1 and 17 work? Do 1 and 17 work? Really? That doesn't seem, that seems weird. No, that doesn't work. Is there an example that is 2 squared plus 1? Or is our next example that we can find a 5 squared plus 1? Is this A times B always 1 more than an odd square? Or can it be 1 more than any square? Is it possible that AB could be 2 squared plus 1? Is it possible that this could be 5? I guess that forces us to choose A and B in a particular way, 1 and 5. Which means we'd have 1 plus 25, which is 26, plus another one, which is 27, and I don't think that's divisible by 5. So that's the only way that we could make 1 more than 2 squared. So what's our next one? Our next one would be 1 more than 5 squared, right? Let's try that one. 1 more than 5 squared would be 26. Maybe that's the pattern. I don't know, right? I'm just trying to grasp at some straws here. Can we find a pattern that works? So 26. So we need factors of 26. We have 2 and 13 as possible. So let's try 2 and 13. Oh yeah, this is totally a mess around night, and I'm fine with that. I feel like most students at the college probably are over finished their exams, So this is our last, I think we have a couple exams tomorrow and a couple exams Friday, but most of the math students I think are pretty much done. $174 is what we get. Is 174 divisible by 26? No. So 2 and 13 wouldn't work, but we could try 1 and 26. As a last resort, that also multiplies together to give us 26. That would be 1 plus 26 squared plus another one, which is 678. Damn, that doesn't work either. So much for that idea. And like I said, I think with symmetry, right, we really only have to try one of them because it's a squared plus b squared plus 1. How are we going to pull out factor 3? This just seems so bizarre to me. How do we make this work?
For a pop quiz.
147. We're getting some easy pop quizzes today. I'm not gonna lie. So we can't make a 5 squared plus 1. That's really interesting. So, I don't know, not seeing like a super obvious pattern. I'm kind of wondering if I should go back and go through the cases where A is even, B is even, and so on and so on. So I'm wondering if we can, again, I might have to go back to the drawing board and just kind of look at cases. And if I can't make it work with cases, then we'll just take a look at what the solution key says, because I'm actually now starting to get really curious about how they solve something like this. So let's take a look at case number 1. If we're going to go through all the possible cases, let's go without loss of generality. Let's take A to be even. Maybe let's not use K because, oh no, I can use K. So let's take A to be even, and let's take B to, why don't we take them both to be even? What if they were both even? If they were both even, we would have an integer, I'm going to call it capital I, where we have 2k squared plus 2m squared plus 1 over 2k times 2m. So if both a and b were even, what happens? We get 4k squared plus 4m squared plus 1 over 4km, 4 kilometers. Yeah, that's not going to work, is it? Yeah, you got it, William. So we know that 4 divides evenly into the 4k squared and 4 divides evenly into the 4m squared, so you're always going to get a decimal number when both of them are even. So we know that a and b, they can't both be even, right? So we're going to run into an issue here. So case 1 is out the window. We can't really work with that. What about case 2? Let's try both of them. Again, I don't really care which one's which, so let's just take both of them to be odd. And see what happens. So if they're both odd, we have an integer value. That is, what, 2k plus 1 squared. So a squared plus b squared plus 1 over 2k plus 1, 2m plus 1. This one looks really complicated. What, we get a 3 in here? We will get a 3 in here, that's true. I'm not looking forward to expanding everything out, but that's okay. So we'll get 4k plus 4k squared plus 4k plus 1, and a 2m squared, no, 4m squared plus 4m plus 1 plus 1. What? It's what we're going to get in the denominator, I think, that's really going to make or break us down here. So down here we're going to get 4km plus... Oh, this looks so messy. I don't know if I want to expand out the denominator, but I'll do it anyway. So plus 2k plus 2m plus 1. It's just really hard to make any executive decisions when you have that inside of your denominator. Blech. But yeah, I agree with you that we do get a 3. We can combine some stuff and make this a plus 3. So what do we know? We know that the numerator is odd. We know that the denominator is also odd. Do we know much else? Question mark. Okay, I'm not sure I got what I needed from case 2, so the last case, again, we'll just go without loss of generality. We'll pick A to be even, let's say, so we just need one of them to be even and one of them to be odd. Doesn't really matter which one we pick. Let's see if this gives us any information. What's going to happen here is we know that we need an integer from squaring A, squaring b, and adding them together, and then adding our 1. And then we multiply a and b. This is our only other possible case. What do we get here? 4k squared plus 4m squared plus 4m plus, ooh, 1 plus 1, so that's even. Well, I guess the denominator is also even too, right? So we get 4km plus 2k. And let's just add these ones up and make this a plus 2. So, can we go through? We could... I kind of like having the factored form in the denominator a little bit more. So I know that I can divide through by 2, so why don't we get rid of this factor of 2? That's so interesting because we get a 2m plus 1 here, and we know that 2m plus 1 has to be a factor of this number. So if 2m plus 1 divides this bit, then 2m plus 1 also has to divide this over here. I wonder if there's something similar like that up here. We can... What if we kept this factored? make any... Are there any 2k plus 1s is what I'm asking. Are there any 2k plus 1s or 2m plus 1s? Any 2k plus 1s or 2m plus 1s? It's not really obvious, right? Or is case 3 is making it a little bit more obvious? So the other thing we can do down here too is that we have k as a factor, so k will have to evenly divide all of this as well. But this is more interesting. So 2k squared plus 2m squared. So is that true? If 2m plus 1 divides that, is that true, or am I making a false assumption here? Is that true? That feels weird because then it's just twice, 2 times the sum of a perfect square, and 2m plus 1 is odd, but the other one's even. But I guess k could play a bit of a role in this too, couldn't it? So I think my logic is a little bit wrong. I don't think that's right. That can't be right. But could we not break this up? Could we not say something like 2k squared plus 2m squared over stuff plus 2m plus 1 over stuff? We could do that. That's a legal move, right? And this factor and this factor are the same. And what's k? K is an integer. So k has to be 1. And if k is 1, now we have an even number divided by an odd number. Oh, what the fuck? No, wait. If k is 1, what do we get? If k is 1, we have 2 over this, right? But that's still an even number. What the heck is going on here? And I suppose the only way to make this work is if m is equal to 0. What the heck, though? That's so weird. I mean, m could be 0. In which case, b is 1. So we just get the solution that a is 2 and b is 1, which we know is, I guess it's true, right? I mean, that works. But there are other even and odd pairs like 2 and 5, right? And 1 and 2. 2 and 5 is another pair, which should pop up inside of this case, right? One of them is even, so k is 1, and m is also, m is 2 in that case. 25, and 4, 29, 30. So why doesn't that work? What am I doing wrong here? Oh. Oh no, I divided by 2, right? I should probably write out all my shit so that I don't fuck this up. I should probably stop taking shortcuts. But I think you still start this the same way. I think, like, you know, you have this nicely factored denominator, so what you do is you put the 4k squared plus 4m squared over this stuff. And you put the 4m plus 2 over this stuff as well. I think that's a legal move. I mean, as long as as long as k isn't 0, but I don't think k can be 0 anyway. That's legal. So over here you factor out 2 and you get m plus 1. Over here you factor out a 2 and you get 2k squared plus 2m squared. A sum of squares isn't helpful. But that does allow us to cancel out some stuff, right? So that gets rid of this. And so what do we know? We know that 2k squared plus 2m squared over... Oh, I see. I wonder if my logic is, like, k doesn't necessarily have to be 1. Because there are probably some values of k where I can add this stuff up. But, so I have to add these two fractions together to get an integer number. But yeah, because they don't have a common denominator, it's hard to see what that looks like. I'm super curious now. It doesn't seem... I thought maybe I could figure it out, but it seems like it's just outside of reach, doesn't it? It seems like it's so close, but I just can't quite... I feel I'm comfortable with case 1. Case 1 can't work, right? They both can't be even. That just doesn't make any sense. Because you can take that modulo 4. But I wonder... I was wondering if we could do something similar here, right? And I mean, I don't know. I don't know if we can take... Is there a... I honestly do feel like this is the most realistic case. I think, like, this is the case where it works. This is the case that makes sense. That's what we've seen, I think. And I was hoping that I could disprove another one of these cases. Like, is it possible to divide through by 2k plus 1 or 2m plus 1? I don't think so. This puts us into the same situation as we have before, which is we have an A, we have a B. And I don't think it's going to work. Okay, I'm just curious now. I'm curious as to what this looks like. Let's take a peek. Let's see. Let's take a look. So either we'll try to get a hint, or if I was way off, we'll just see what they say and we'll roll with it. Okay, so by definition, we've shown that f of 2, 5 is 3. I believe that's what we had. we, by definition, blah, blah, blah. So for this to be an integer, it must be that 1 over a squared is an integer. And the only positive integer is 1, so that was good. So here it is. So part C. Suppose a and b are positive integers, and our function is an integer. Oh, they do contradiction. Okay, so assume it's not a multiple of 3. Okay, I was wondering if you could do contradiction. Hot dog. Okay, so that's the solution to the problem, is to just find the contradiction. Okay, so let's see what they do. Okay, so by definition, yep. By multiplying by AB, that's what we get. And they rewrite it. So they rewrite it as a squared minus kba plus... Oh... Got it. Okay, I see. I see. They turned it into a discriminant problem, didn't they? We were so close. So if you take this as KAB, a squared plus b squared plus 1, and you say 0 is equal to a squared minus KBA plus the rest of the stuff. Darn. So A must look like negative B plus or minus. It's negative B, it's B squared minus 4AC, right? B squared. So B squared minus 4 times 1 times B squared plus 1. So 4AC over 2A. And so the question is it possible? Is it possible to... This is 4B squared minus 4? Does that factor? Is that a perfect square? That could be a perfect square. Doesn't look like it though. Okay, so I'm happy with that. That makes sense. Since A is an integer, okay, then they're looking at the discriminant. Oh, I see, I see. So for A to be an integer, we need k squared b squared minus 4b squared minus 4. This has to be a perfect square. Is that how that works? So if this is a perfect square, we'd be good to go. Is it obvious how to make that into a perfect square, though? I still think there's a fair amount of work to do here. Still not obvious. I understand their logic, but it's still not obvious, so that must be a perfect square. So rewriting the discriminant. So what are they going to do? They're going to factor out b squared, factor out the difference of squares. Okay, I can get behind that. Oh, and then they're going to start trying to make their contradiction. Wow, this is a crazy problem. I like it. Since k is not a multiple of 3, since it's not a multiple of 3, then it's either 1 more than a... Yeah, so it's either 1 more than a multiple of 3 or 2 more than a multiple of 3. Sure. one of these things is going to be a multiple of 3, right? A multiple of something like 4, if I add 2 more to it, it's going to end up being a multiple of 3.
Oh yeah? Prepare to be iterated.
What is this? Thank you very much for the follow, Lily Y. Ada. Thank you very much. Welcome to the Epsilon crew. If you have any mathematics questions and or concerns, feel free to get them into the chat. We can talk about that tonight before I peace out and have a nap. What about the k-2 though, right? That must be the one where if we have something like the number 5 and we take 2 away from it, we're going to get back to a multiple of 3. So k-2 or k+2 must be a multiple. One of these is a multiple of 3. That's what they're going to argue, right? Yeah, so one of them has to be a multiple of 3. And then you can replace this with a multiple of 3. So they're going to replace this with 3m. So we can replace the discriminant as b squared times 3m minus 4. Where did their plus 2 come from? There's a lot of weird algebra happening here, but that, I mean, I agree with them, and that's fine. So yeah, so it should be b squared times a multiple of 3 minus 4. In other words, the discriminant itself is 2 more than a multiple of 3. And this is true. This is a number theory fact, right? Either the perfect square is a multiple of 3 if 3 is one of its prime divisors. Otherwise, it's going to be one more than a multiple of 3. Yes, that is true. And so they proved that here for us. So the determinant, we've determined that the discriminant is a perfect square and is 2 more than a multiple of 3. The determinant is a perfect square 2 more than a multiple of 3. That's your contradiction. Wow, what a crazy contradiction. There's no way that I would have just like randomly figured that out if I was a grade 12 student like writing the Euclid 2019 contest. Thinking back to what I was doing in grade 12, man. That's some pretty intense number theory. It's kind of crazy. Should we look at the last part of this question? I'm scared now. So we failed miserably, part C. So determine 4 pairs of positive integers where a and b both have to be bigger than 2, for which FAB is an integer. That's wild. All of the ones that we have so far do not work, right? We have 1, 2, we have 2, 5, and we have AA, I guess. But B has to be bigger than A. So that's interesting. I guess next time we get together, we go fishing. We're gonna go fishing for some pairs of integers and see if we can find, we have to find 4 pairs. We really only have to find 2 pairs though, right? Because or no, wait. A has to be less than B, so that sucks. Even if we find a pair that works for A and B, we can't swap the numbers around. So we're gonna have to find 4 unique pairs the next time we get together. That's crazy. Before we go tonight, though, I'm gonna dive in and see what Andy's been up to. Andy has been just going ham on a bunch of stuff, and I'm wondering if there's something kind of simple that I can kind of wind down to that's not super crazy to think about. Folding to units. This seems like okay. So given a strip of 6 equilateral triangles, is this 6? 1? No, this is a strip of 10 triangles. How many folds are necessary to reduce it to a single equilateral triangle? You can fold only along the lines. And if you can solve it, try starting with a different number of triangles. What has this been going handy? He has been, yeah, he's been going ham. Puzzle Hamdy. So, okay, so if we have a strip of 6 triangles, it's not... It's obviously not 6, right? It's obviously not 6. But... Okay, let's just pretend. It's obviously one fold.
Time for a pop quiz.
That has to be 2 folds, right? I think where it gets interesting is when we start kind of adding some more. So let's see, if we start to add some more, so now we have another even number of triangles. We could, but you have to fold along the grid lines. Like, isn't this still 3 folds? Like, I don't think you can get out of that. I think it still has to be, if you have 3 triangles, 2 folds, yeah, and if you have 4 triangles, there are 2 options for the first fold, both of which reduce the strip to a 3 triangle strip. Right, so either you go here. Yeah, I think you're forced to do 3. I think that makes sense. That makes sense. I'm happy with that. But what about 5? Here's where things might start getting a bit interesting. So 1, 2, 3, 4, 5. Because you could collapse these 2 together. Right, so like what if we started with this fold? That'll get us to... We'll still have these ones, right? But that's going to move this triangle over here, right? And then we could fold here. And then things are over top of each other. So this one also only needs 3 folds, I think. I think you can sneak away with 3 folds here. And now I just really want a croissant. But I think that this is 3 folds, right? There are 2 options for the first fold. Choose the option closest to the middle. Fold it in half, it becomes a 2 triangle strip. That makes sense. I'm happy with that. One, 2, 3, 4, 5, and 6. Do we always take what's in the middle, or is it going to bounce back and is it going to be dependent, I guess, on whether or not we have an odd number of triangles or an even number of triangles? So it goes 1, 2, 3, 3. What about 6? What if we did take a middle fold? Like, what if we folded here? That's going to collapse these 2, right? And it's going to put this one here. And then another one over here. Something like that. And then we could probably fold like along here. This seems super intense. Like, this is really hard without actually having things to fold. My brain is hurting. But that would pretty much narrow us down to something that looked like this. And then there's going to be 2 more folds here, which would kind of suck. So 1, 2, this would be 4 folds. So is it possible to make that I don't know, 4 folds seems reasonable. For 6. I found this by simply trying all of the possible ways. What a guy. Okay. Okay, I can get behind that. So 1, 2, 3, 3, 4. And then he did it for 10 triangles. I think it's gonna come down to if you can make really nice arrangements like what we did here, if you can make it somewhat symmetric. I think it's going to be easier to do that with, you need an odd number of triangles to make it symmetric, right? Like if we had 7, would it work with 7? 1, 2, 3, 4, 5, 6, 7. Could we fold this to make it symmetric? Like if I folded here and I collapsed these 2, what would we have left? We would have our original 1, 2, 3, 4. We have the original 4. That one would flip over. Oh, so maybe it doesn't work with every single odd number. Maybe there's only certain odd numbers where this is going to work. But then we're going to have basically like a new one up here. Like if this one goes to here. And then you're going to have like this extra one popping out like that. Now it just kind of looks like a duck. And that's with 7. So there was something interesting about 5. Oh, because when you take away 1, you have an even... Oh, maybe it's a square number. I think it would be the same over here, right? If I decide to fold here and collapse these 2, I'm going to have one side that has 1, 2... Yeah, 1, 2, 3, 4, and one is going to have 4, one is going to have 2. So it doesn't quite break it down nicely. Interesting. Because ideally what you want is you want that first fold. But this is, I don't know, it's still kind of nice because you can still fold here. Right, and get mostly, that'll collapse all of this stuff together. I don't know, this one's a little hard for me because I find it really hard to maneuver stuff around mentally. Goodness gracious. I am curious about his 10 though, so 6 folds question mark. So he has the possible folds. Crazy. I wonder if there's actually a way to figure out how many folds you would get. I'll zoom it in so you can see the possible folds. But yeah, my intuition is you're going to want to make a fold first that's closest to the middle. And you ideally want to get symmetry, don't you? Which is kind of what he has with, like, why wouldn't you do the second fold right here? I guess because then you get stuck with 1, 2, 3, 4, 5. You get stuck with 5. And we know that if we're stuck with 5, it's going to take us 1, 2, 3, 4. It's going to take us 3 more folds to do. No, I don't know. If you fold it once and you fold it twice to get 5. Oh no, it won't work. Yeah, because folding it along there won't necessarily make it work. Oh man, okay. Too hard for me. I wanted something that was going to be easy, but that was definitely not easy. I might piece out. I'm going to piece out of the folding triangles around. But anyway, thank you very much for coming and hanging out, guys. Let's see. My tomorrow looks a little less chaotic than today. So I think most of my shit happens in the morning tomorrow. So I should reasonably be able to either do a 5 o'clock or 7 o'clock tomorrow night. Yeah, I'm throwing the towel in, throwing it in. No more folding for me tonight. I'm done with the folds. Yeah, I can't do it. It's too much to handle like in my brain, right? And it also just doesn't look like there's a nice easy pattern you can use because you have to really maneuver stuff around. Oh well. You win some, you lose some, right? You win some, you lose some. So I'm going to sign off for the night. I got to go have a little bite to eat and take care of the pups. So I will be back tomorrow, hopefully around 5 o'clock if things go well with all of my meetings tomorrow. And if not, it'll be a little bit later. We might push it back to 6 or 7 p.m. And my goal, I think, tomorrow night will be to look at the last part of question 9 on our Euclid contest. So I'll post the link to the Euclid contest so you guys can take a look at 9D. But I think that's what I'm going to try to do tomorrow night. We'll try to solve 9 tomorrow night and see if we can make any progress on 9D. Thanks, Lawrence, for swinging by. We'll see you guys soon. Take care.